Hello minions, MoNaCo here, and Milks. Getting real close to the end of this video.
That's it.
Yeah, we got like maybe one more. Is this the last one?
This is the last one.
This is it?
Woohoo!
Whoa! 12 videos in this unit. Not too shabby.
Well, we had a bunch of little ones that not anything. We had to build.
You're welcome.
Yeah, but we had to build some ideas to get to these big ideas like this. Now, this is a major conceptual idea that we're only going to have so much practice at,
and it's testable too.
But that's the thing, is it is testable. This is, theoretically, these ideas that we're going to do in this few pages is huge.
Yeah, it's the reason why we're all here today. Entirely honest. In
Really?
my personal opinion, which I'll let you in on when we get there.
Yeah, but it's the culmination of everything we did this unit really leads to this one big idea.
Yeah.
So IMF stands for Intermolecular Forces. So what happens when one molecule feels another molecule?
Yeah. What happens when two molecules get close enough to do something to each other?
Right.
What is that though?
Can they affect each other?
Can this molecule over here have an effect on that molecule over there?
Could.
And what is the effect? How do they play together?
Right. Do they play nice, or do they like each other too much?
Right. We've been mentioning this throughout the unit in terms of like ionic compounds are oppositely charged and they're attracted to each other.
Yeah.
And covalents can have this polarity in their bonds and their molecules. We're talking about the intermolecular forces of attraction that are a result of these attractions and repulsions in ionic compounds and covalent polar molecules.
Right. So last video, we talked a lot about the polarity of a particular molecule.
Right.
And again, in this particular diagram on the left, you can see that the two vectors, if you will, cancel each other out.
Or the dipole in the bonds. So the
now
polar bonds.
I don't have this like positive end and this negative end. So it doesn't exist. So this particular molecule of CO2, when it gets next to another CO2 molecule,
it doesn't care.
It doesn't have any magnets to stick.
It might bump into it, but they don't get stuck to each other at all.
They don't have an affection.
Right.
They're not even like
attracted,
infatuated with each other, or obsessed like you could get when you get something like this, where these two vectors,
they compound each other.
Right, like they double it up to make it go like this.
Right. You can see that molecule of oxygen there has most of the electrons on the O side of things.
Right, so that's going to give me that partial negative and that partial positive side. And that partial positive, I'll draw that in real quick. This side is going to be that partial negative. Down here, I'm going to get this partial positive. And we all know that positive and negatives attract.
So if I have two or three of these water molecules with a molecular dipole, the positive end of one water molecule can line up to the negative end of the other water molecule, and they're kind of okay like that. It's kind of like they line up like a conga line, front to back, front to back, front to back.
They're really happy like that, yeah.
It's like, magnets-ish.
Yeah.
And that's the nature of an intermolecular force.
And that's really what's going on here. So the positive end of one molecule is attracted to the negative end of another. You can see that in the picture here, the partial negative, partial positive.
Right.
Notice they're kind of facing in opposite directions.
Right.
And they're happy.
Opposites
attract. This is called a dipole.
This is, a dipole attraction is what I would call it.
Right. Yeah, a dipole or a dipole. Right.
Dipole attraction. Dipole.
So on the other side, we don't get into this very much, but if they were to flip the other way,
which they do when they're rolling past each other,
the positive end of one now is not attracted to the positive end of another, and it makes them actually probably move a little bit more apart. It gives them a little bit of a push.
We don't give this an actual name because we're always usually talking about intermolecular forces of attraction. So when we say dipole, that's two polar molecules attracted to each other, lined up, head to tail, head to tail, head to tail. It will on some things. So let's physical and chemical properties of these things. Let's see. Let's get it.
So number one, hydrogen bonding.
The beast.
This is the big one.
This is the one you got to know. If there's one intermolecular force of attraction that you know, it should be hydrogen bonding.
Right.
If there's two, it should be ionic charges attract.
Right.
If there's three, it should be that other things out there can have dipole attractions.
Right. I like to think of this hydrogen bonding as basically a dipole on steroids.
Right. And there's a very rare, it's not rare, but it's very strong.
And there's some very specific
rules to it.
So here we go. Hydrogen bonding is specifically when the dipole is between the hydrogen of one molecule,
Mm-hmm.
the hydrogen atom of one molecule, it gets near the specifically nitrogen, oxygen, or fluorine of another molecule. And in all three pictures here, we can talk our way through how that's happening. So let's do that.
So the hydrogen, being less electronegative than the oxygen, nitrogen, or fluorine, loses out on the tug of war for the electrons in the bond. So this polar bond here has a net dipole moment pointing in this direction. But the molecule itself has a net dipole where there's the partial negative on the oxygen side and the partial positive on the hydrogen side.
Right, you can see them in the picture.
Mm-hmm. For sure. And this picture also shows it there. So the hydrogen's partial positive, the oxygen's partial negative, and we're still talking about a water molecule.
Right. Let's finish the first picture then.
Okay. The first picture. So now we have another water molecule rolls up on the scene and says, well, if you've got a partial positive end, I'm going to line my partial negative end up towards it. And this dotted line here, is that a force of attraction between the oxygen, partial negative on one molecule, and the hydrogen, partial positive, on another molecule?
Now, because you drew that as a dotted line, I'm going to go right for this piece. Ready? It's not a true bond. It's a strong force of attraction.
There's no actual sharing of electrons.
This is,
here.
I feel you very strongly.
This is also referred to sometimes, and not so much anymore, as a coordinate covalent type bond. Right, Mr. Milks?
No.
It's when one...
We really should teach that coordinate covalent bond.
Mhm.
That's different. That's an ammonium ion when it's got the lone pair. and
Well,
then
I
the
thought it was
hydrogen
with lone
ion comes
pairs.
up.
Ammonium's NH nitrogen. So there you
But
go.
it's NH4, and that H plus ion comes over onto the lone pair.
Okay.
When I share a lone pair, that's a
Yeah,
coordinate
okay.
covalent bond.
I like to think of it as like,
But these lone pairs are affecting that negative side. So you're right. It's
an attraction
doing it,
to the
but it's
negative
not
pair
a-
of electrons.
in a
out there.
coordinate covalent bond. They're actually sharing electrons,
They are?
just not evenly at all.
Okay, so this is not a coordinate covalent bond like
No,
I
it's
thought
not.
it might
No,
have
it's
been. Okay.
That's okay. We really should
The
do that.
concept is there. That's why I thought. it
There's
was
a carrot. Why don't you ask us in class what a coordinate covalent bond is so we can clear that up?
Yeah. So back to hydrogen bonding.
Let's get back to that.
Because we got off track there.
Yep, so right here.
It's not a true bond. It's an attraction between a partially positively charged hydrogen in a molecule
Yep.
and a partially negatively charged oxygen, nitrogen, or fluorine in a different molecule.
Right, so why don't you circle the hydrogen on that first there, and then circle the oxygen for us so we can see that that's where that dotted line is happening.
Right.
And we can do that same thing real quick in the next picture.
Right. Now this is a hydrogen on one molecule and a nitrogen on another. Again, attracted enough because nitrogen's super electronegative, wants to steal electrons. Hydrogen's been de-shielded and pulled away from by oxygen. And let's see here, this last one, we got a partial positive on that side and a partial negative on that side. So we've got a polar molecule for sure.
Yep.
And so the hydrogen here, if we do another HF involved,
There we go.
get attracted to this end of the molecule.
Right, and that would be the hydrogen of one molecule attracted to the fluorine of another molecule.
Attracted to the lone pairs of electrons hanging out.
Yeah, but
on
what we're looking
oxygen,
for
nitrogen,
is
fluorine.
hydrogen on one, nitrogen, oxygen, or fluorine on another.
Okay. Hydrogen bonding, Mr. Milk, so what? Who cares? Big deal, whoop whoop.
Well, it does some really interesting things to some things we like water, specifically. So, because those positive and negative ends hook up so much, it makes the boiling point of water actually relatively high
For a covalent compound.
for a covalent compound. At 100 degrees Celsius
It's actually kind of hot.
relative to all the different alcohols and other organic molecules. that would be
Covalent
liquids.
compounds of similar molecular size.
Even that too.
So, I mean, water is only 3 atoms. H, 2 H's, and 1 O. Anything else out there that's covalent, nonpolar, no hydrogen bonding that's got 3 atoms in it is like a gas at room temperature.
Right, not even a liquid.
Not even a liquid, right?
Right.
And so the fact that water melts at 0 degrees Celsius, which is comparatively high for small covalent molecules, and boils at 100 degrees Celsius, which is almost unheard of for small covalent molecules, hydrogen bonding is what's creating that situation.
Right, there is such a strong form of attraction with the water
Right.
that even if you were to put it on the table,
It beads up.
It beads up, and it doesn't just evaporate right away.
Nope.
They really like to hang out with each other, and this is why that positive,
Hydrogen
negative.
bonding.
Yeah.
Now the density is another kind of a big deal.
No, we studied density earlier.
Everybody knows that ice cubes float in your
Right.
glass of water. This is kind of messed up when you think about
Right, I'm
density.
going to go right out there. I'm going to say, isn't water like basically the only solid that is less dense than its liquid?
Correct. Usually when you cool something down to make it a solid, the atoms get packed in closer together. It gets more dense and it
Because I got more
sinks.
stuff per space.
Yeah, they've got more mass per unit volume. So it would sink normally.
Right. But the density of water is actually lower than the solid form of water, and that's partially to do with this hydrogen bonding. And if we look at the picture,
It's also why water forms crystals.
yeah, which are weird.
Snowflakes.
Cool,
It
the
snowed for the
shards.
first time last
Right.
night.
If you look at this, like the water, you see how they're all rigidly lined up,
In that hexagon kind of pattern in
which
three
is that
dimensions.
crystal, right? And then if I go to liquid, they can really get much closer in on each other and get more of them in less space.
Right.
That's how they become more dense.
It's not much denser, but it's enough
That
to
the
make
solid
that
floats.
so that the solid floats, which I personally think is kind of a big deal, because if you believe biologists, they say evolution and life originated in these tidal pools on the edge of the oceans and stuff, and like in pools of water that got isolated
Right,
from the ocean.
very simple one cell guys.
Simplest stuff. Well, imagine a pool of water inland somewhere that freezes up in the night and the ice falls to the bottom. What would it do to all living organisms in the bottom of that pond?
Would have crushed it.
It would have crushed them to death. They would not have evolved over time. Another thing, the Great Lakes, right across our doorstep up in Charlotte, the Great Lakes freeze over every now and then.
Right, almost all the way.
Almost all the way. And that layer of ice actually begins to insulate the little fishies underneath.
Right.
The water underneath the ice is actually warmer than the ice at the top anyway.
Right, it does insulate it so that the water can't get any colder.
It can't get any colder. The fishies underneath get cold, but they actually can still survive.
Right, because they're cold-blooded.
So we humans, even if you believe other alternate theories of why we're here, the fact that the ice floats is really important, even to us just going fishing and feeding ourselves.
Right.
Ice freezes, falls to the bottom, crushes all the life in the lakes. There's no fish to eat.
Right.
No fish to eat, no frogs, no amphibians. All of a sudden,
We got many life cycles.
many life cycles are connected to the water.
All right, so let's wrap this last video up. Ready?
Yeah, done.
Two polar molecules get near each other. We're going to call that dipole-dipole.
Yep.
Pretty wide spectrum of that happening can happen. But then, the very specific one to know,
When hydrogen of one molecule gets close enough to nitrogen, oxygen, or fluorine of another molecule, we call that hydrogen bonding, which is dipole-dipole on steroids.
right. So what's so specific here? In the hydrogen molecule, I'm actually going to take a quick second, right?
Okay.
If I draw water, and I got H, I got O and H,
Look at these.
right? This is not a hydrogen bond.
No, that
That's
is a
an
covalent
actual bond, right?
Hydrogen bond is not actually a bond.
But mister, that's between an O and an H.
Yeah, but this is a force of attraction between the H of one molecule and the nitrogen, oxygen, or fluorine of a different molecule. So there's another molecule of water. Do this in red. Do it in red. This dotted line that he's about to draw from the hydrogen over to the oxygen there is not actually a bond. It is a force of attraction, which was the focus of this entire video.
Right, and I get it. It's called hydrogen bonding, and you're going to get mad. I get it, but it's just how it is. I didn't name it.
Right? Hydrogen, dipole. That's what it should really be saying.
Right, seriously.
Yeah.
And then there's one other one we didn't really talk about that does happen. I just want to mention it so we do due diligence, okay?
London dispersions,
Yep.
aka
If I have if I have two non-polar molecules, that's the best they can get, is this momentary change in electrons that happens that creates this false positive negative.
and we're talking femtoseconds. Here.
Yeah,
It doesn't
really.
happen
No.
at all.
No,
Really.
It just happens because they happen to bump into one another and they kind of move.
React.
Yeah.
The electron clouds around the molecule reacts when they get close enough to somebody else.
And then they fall right back to where they're
go back
supposed
to where
be.
they wanted to be.
It's very, very weak, and so we're not going to get into it too much, but I just wanted to take the opportunity to tell you about
That's
it.
why nonpolar molecules can be dense and stuff like that. That's a look. So, 14 minutes.
Sorry it took so long, but this was a
Last one.
major important concept.
And we got out in the weeds a little bit there with
Well, but it was good.
necessary. Thanks for watching. Next unit starts soon.